This lecture is on blood vessel physiology, part 3. In the last lecture, we talked about blood pressure and some of the factors that affect your blood pressure. What we're going to talk about now is how blood pressure is regulated over the short term. So there are different homeostatic mechanisms that help regulate blood pressure over the short term. They mainly work by regulating the blood vessel diameter. So the main way short-term mechanisms work is they change the diameter of the blood vessel. Now, of course, if you make the blood vessel smaller, that increases the peripheral resistance, and that's going to increase your blood pressure. If the diameter of the blood vessel gets larger, that's going to decrease peripheral resistance and drop your blood pressure. So again, this is the main way. Also, heart rate and contractility are changed also to regulate blood pressure. So why regulate blood pressure over the short term? Well, the main reason is to maintain homeostasis, a stable internal environment. More specifically, it's to alter the blood distribution to make sure that every organ gets the blood that it needs at that particular moment in time. So again, it's to ensure that those organs that need the blood, they need the oxygen and the nutrients at a particular time, get it. The other reason is to maintain adequate mean arterial pressure, for example, so that you don't faint when you stand up. So remember that when you stand up, gravity causes the blood to rush from your brain to the lower parts of your body, which could result in you fainting. But because of short-term regulation of blood pressure, that doesn't happen. Now, what controls short-term regulation? Well, it is the two great controlling systems of the body, which would be the nervous system and the endocrine system. Let's focus on the nervous system first. The main way that the nervous system controls your blood pressure over the short term is by changing the diameter of the blood vessel. Okay? And remember, by doing that, you affect peripheral resistance. Remember, blood pressure equals cardiac output times peripheral resistance. Peripheral resistance is one of the main factors that affects your blood pressure. If peripheral resistance or friction goes up, your blood pressure goes up. If peripheral resistance or friction goes down, your blood pressure goes down. The specific mechanism that the nervous system uses to control your blood pressure is a reflex. Now remember from A&P1 that a reflex is a rapid, predictable, meaning the same thing happens every time, and involuntary response to a stimuli. Okay, and as a reminder, there are 5 components of the reflex arc. So first you have, in this particular situation, you can see the stimulus here happens to be a nail. So it would be pain. Maybe you stepped on a nail, your foot. There's a nail in your foot, so there's pain there. The first component is the receptor. And the receptor is picking up on whatever change is occurring. So again, it could be pain, it could be pressure in your blood vessels, it could be heat on the surface of your skin. The receptor is the first component, and then you have the sensory neuron that's bringing the information to the integration center. Now in this case, the integration center is the spinal cord, and of course made up of interneurons. And then you have the motor neuron, which brings the information out to the effector. In this case, it's a muscle, and it's the same effector in blood vessels, except it's smooth muscle. So let's start with the reflex arc, and the first thing is the receptor. There are many different types of receptors in your body. Some measure changes in certain chemicals. Some measure changes in pressure, such as the baroreceptors. So the baroreceptors are actually measuring changes in the pressure of your blood in the arteries. And they are located mainly in large elastic arteries. So let's take a look at where you find them. Here's the heart, and you'll notice the aorta. These green areas are areas where the baroreceptors are clustered. So you can see them at the entrance or the exit of the aorta from the heart, in the ascending aorta, and also in the aortic arch. And this is a good place to have them because this is when the blood pressure is at its highest coming out of your heart. And then if we go up here, we see the right common carotid artery. Now, whenever you see the word common for an artery, it means it's going to split into an internal and an external. So here we have the internal carotid artery, which goes to your brain, and the external carotid artery, which brings oxygen and nutrients to structures in your face and neck. Right here, where the split occurs, there's a widening of the internal carotid artery. This is called a sinus. A sinus is when a blood vessel is wider in one area. And here's where you find a bunch of baroreceptors. Now, this is a good place to have them too, because the internal carotid artery serves your brain. And that is a very critical organ, and you would want to be monitoring the blood pressure going to the brain. Now, the role of these baroreceptors is to protect the body against short-term changes in blood pressure. Short-term, for example, when you're going from lying down in bed in the morning to standing up. That's a short-term change. How do these baroreceptors actually work? Well, in this figure, we are looking at a normal scenario. So we're assuming this is homeostasis. What do the baroreceptors do under normal situations where your blood pressure is not too high? Well, if we looked in the brain, in an area of the brain called the medulla oblongata, this is where you would find these baroreceptors. Now, the medulla oblongata is where a lot of visceral functions are housed in the brain, such as regulation of heart rate, breathing, blood pressure, vomiting, and things like that are all controlled in the medulla oblongata, which is part of your brainstem. Within the medulla oblongata, we can find these cardiovascular centers, and there are 3 of them, as you can see here. The first one is called the cardioinhibitory center, and note the word inhibitory. It is part of the parasympathetic nervous system, and remember that this is often called the resting and digesting division. So remember that nickname. So the cardioinhibitory center contains neurons that send their action potential through the vagus nerve to the heart. That's the heart. When they send an action potential to the heart, how does this division affect the heart rate? Now remember, it's the parasympathetic nervous system, the resting and digesting. So if you guessed it decreases the heart rate, you would be correct, and thus decreases the cardiac output. Remember that cardiac output equals stroke volume times heart rate. So if the heart rate goes down, so does the cardiac output. If your heart rate goes down and your cardiac output goes down, then your blood pressure goes down. So normally the cardioinhibitory center lowers your blood pressure. Now the cardiac-accelatory center, and notice the word accel here, is part of the sympathetic nervous system. And remember that this is nicknamed the fight or flight division. Neurons in the cardioaccelatory center send their action potential through sympathetic cardiac fibers. And these travel again to your heart. So how do they affect heart rate? Well, it is the fight or flight. They are going to increase your heart rate. They also increase the contractility, or the force with which your heart contracts. If the heart rate goes up, remember this formula, the cardiac output goes up and the blood pressure goes up. So the cardioaccelatory center, when it's normally active, increases your heart rate. And lastly, we have the vasomotor center, which is part of the sympathetic nervous system also. The vasomotor center sends its action potential through the vasomotor nerve, and this actually travels to blood vessels. There's a blood vessel. And it targets the smooth muscle in the blood vessel. So we're really talking about smooth muscle. What it does is it causes vasoconstriction. Now remember, vasoconstriction makes the diameter of the blood vessel smaller. Okay? And if the diameter decreases, the friction increases, and that means the blood pressure increases. So normally the vasomotor center, when active, will increase your blood pressure. Okay, so again, this is the typical situation. These are how these centers in the medulla oblongata typically operate. Cardioinhibitory will typically decrease your blood pressure. Cardioacceleratory will increase your blood pressure. Vasomotor will increase your blood pressure. Now, the baroreceptors, they are going to connect and send action potentials to these centers if necessary. So let's see when it would be necessary. Now, this looks a lot like the last one, but notice up here, the scenario here now is your blood pressure is too high. When it's too high, the baroreceptor is going to send messages to these centers. And the message it's going to send is it's either going to stimulate or inhibit these centers. Stimulate or inhibit. So if your blood pressure is too high, would you want to stimulate the cardioinhibitory or inhibit it? Now keep in mind how this affects your blood pressure. Well, if you said stimulate, you would be correct. So when your blood pressure is too high, you want to stimulate this and cause it to send action potentials to your heart, right? Which is going to decrease your heart rate and decrease cardiac output. That will decrease your blood pressure. And you might think, okay, that problem solved. It was too high. The baroreceptor stimulated the cardioinhibitory center. Now it's low again. But it doesn't stop there. The baroreceptor is going to send a message to the cardioacceleratory center. Would you want to stimulate or inhibit the function of the cardioacceleratory center? Well, you would probably want to inhibit it. Because normally, remember, it's going to send action potentials through cardiac sympathetic fibers to the heart and increase your heart rate. But you don't want that to happen. So if you inhibit it, it's going to decrease the heart rate, decrease contractility. Now normally, again, it does the opposite, but you are inhibiting it. And so that will lower your blood pressure. So now we're doing two things to lower your blood pressure. Now lastly, the baroreceptor is going to send a message to the vasomotor center. Now remember, normally this center causes vasoconstriction. So the baroreceptor is going to inhibit this center also. And so what's happening is basically less action potentials are being sent. And instead of getting vasoconstriction, you end up with vasodilation. And of course, that decreases friction, which results in decreasing your blood pressure. So you can see here, it might seem redundant to do all three of these things since it seems like one would be sufficient, but it's not. The baroreceptor is affecting multiple cardiovascular centers, and by doing that, it brings a very quick change in a very short period of time to your blood pressure. So this next slide is from a textbook, and the top is kind of just going over what we did. What happens when the blood pressure is too high? Okay, so I drew that out on the prior two slides, and this just shows it to you in another way. But down here, it's showing you what happens when the blood pressure is too low. Okay, so you'll notice here, this little seesaw is, if it's not perfectly straight, it means you're out of homeostasis. So here, your blood pressure is too low. Now in this case, what happens is the baroreceptors just aren't triggered. They only get triggered when the blood pressure is too high. And so they send fewer messages to the cardiovascular center. So think of about fewer action potentials or less frequent action potentials. And when that happens, the cardioexcitatory centers are not inhibited. And so you get vasoconstriction from the vasomotor center, you get increased heart rate, increased cardiac output from the cardioexcitatory center, and the cardioinhibitory center is also working, but not at the same level. So what that does, since these cardioexcitatory centers are more dominant, is it raises your blood pressure. So again, when your blood pressure is too low, the baroreceptors are inhibited, and the frequency of action potentials they send to the vasomotor center and the cardiovascular center are lower, and so these become more active. Okay, so that's how the nervous system controls your blood pressure over the short term, but the endocrine system is also involved here. The endocrine system uses hormones. I'm going to mention a couple of hormones that affect your blood pressure over the short term. And I also, just to go back for a minute, in terms of baroreceptors and the nervous system, baroreceptors can't protect you from long-term changes in your blood pressure. So again, we're only talking about short-term changes in blood pressure. If your blood pressure slowly rises over time, for various reasons, you get older, you gain a lot of weight, you have atherosclerosis, and it rises to a higher level, your baroreceptors will just reset to that higher level. And they will say, oh, 140 over 90, that's the new normal. And now we won't kick in until you, exceed that level. So again, baroreceptors just protect you over short-term changes in blood pressure. The endocrine system also does that. So the first two hormones, which we often talk about together, are epinephrine and norepinephrine. And the source of these hormones, if you remember, is the adrenal medulla. So here are these hormones coming back. The target, there's two targets. The first is the heart. And in the heart, there are receptors which are called beta, and that's the symbol for beta 1 receptors. Okay, so these are on cardiac muscle, these beta 1 receptors. That is the target of epinephrine. Also, arterioles are the target of epinephrine and norepinephrine, so the teeny tiny arteries. Now, the effects on your heart is it increases your heart rate, and which, of course, is going to increase your blood pressure. The effects on the arteriole is to cause vasoconstriction. So the two of these together result in an increase in your blood pressure. Okay? Now, if you've ever heard of pharmaceutical drugs called beta blockers block the beta 1 receptor on the heart. So if somebody has a unusually high heart rate or high blood pressure, you can use beta blockers to lower the heart rate and lower the blood pressure. So if you ever heard of that term, that's where it comes from. Another hormone which we have not discussed is atrial natriuretic peptide, or ANP for short. Now you can learn a lot about this by looking at the name. Atrial, what does that sound like to you? If it sounds like the atria of the heart, you are correct. And that's actually where this hormone is made, the atria of the heart. Now that's a little strange. We don't think of the heart as an endocrine gland, and it's not, but it does have some endocrine tissue in the atria. The target of ANP are arterioles. And there's one more target, the kidneys. What ANP causes is it causes vasodilation of the arterioles of the heart, which is going to result in a decrease in blood pressure. But it also targets the kidneys. Now here's where you have another clue. Uretic, uresis, urine. Where is urine made? The kidneys. Natri, on the other hand, is short for natrium. And natrium means sodium in Latin. In fact, the symbol for sodium is Na, right? Na, natrium. So this refers to sodium and this refers to urine. The target of ANP is also the kidney. And what it does is it causes the kidney to release sodium into the urine. So the kidney filters your blood, and as it's filtering the blood, it filters out sodium. And wherever sodium goes, water follows. So you end up with a lot of water in your urine. Okay, that means there's less water in your blood, and that means your blood volume drops. So if your blood volume drops and you get vasodilation of most of your arterioles, what's going to happen to your blood pressure? Well, it's going to go down. And that's how this particular hormone works. Two more, antidiuretic hormone or ADH. Remember that this is made in the hypothalamus. The target is the kidneys, again, and also arterioles. Now the effects on the kidney is kind of the opposite of ANP. It causes water to be reabsorbed back to the blood. Okay, so again, as the kidney is filtering your blood, it's going to take that water back and keep it in the blood and not let it go out into the urine. This is going to cause your blood volume to increase. The effect on arterioles is going to be vasoconstriction. In fact, one of the other terms that people use for ADH is vasopressin, because it increases your blood pressure. Or vaso, you can think pressing on the blood vessels. And so both of these things are going to increase your blood pressure, okay? This is antidiuretic hormone. So if this is confusing, diuretic is a word for diuresis, which means urination. So we have anti-urination, which means it's prohibiting the loss of water in your urine, and it's keeping that water where? It's keeping it in your blood vessels. And so you've got a greater blood volume, and the greater blood volume, the more friction, the higher the blood pressure. Okay, the last hormone I'm going to mention is aldosterone, and aldosterone is made in the adrenal cortex. Remember, this is the outside of the adrenal glands. The target are tubules in the kidney. Now these tubules are where urine is released, and they are impermeable to water normally, impermeable. So what aldosterone does is it increases the reabsorption of sodium. And you notice sodium is an ion we're seeing a lot here when it comes to urination, back to the blood. So instead of letting the sodium go out in your urine, we're reabsorbing it back to the blood. And remember, wherever sodium goes, water follows because of osmosis. And so what happens to your blood volume? So you're getting more water back to the blood, it goes up. And if the blood volume goes up, blood pressure goes up. Okay? So most of these hormones I've mentioned increase your blood pressure with the exception of ANP. So that's hormones, but there are also endogenous chemicals found in your body that also regulate your blood pressure. Now, endogenous is just a word that means naturally found in the body. And there are two I'm going to mention because they're really powerful. The first one is nitric oxide, or NO, and the strange thing about this one is it is a gas. So think about this. This is a gas, and the source of nitric oxide is actually the endothelium, which, remember, the endothelium is the tunica intima in blood vessels. So this is where it's made. It is a powerful vasodilator. It is a powerful vasodilator. So if your blood vessels increase in diameter, what happens to your blood pressure? It goes down. Now, nitric oxide, this is a very temporary effect. As you might guess, it's a gas. Blood vessels release it, and your blood pressure drops. Endothelins, on the other hand, they are also made in the endothelium. Okay, so that's the tunica intima of all blood vessels. And their effect is they are a powerful vasoconstrictor. In fact, one of the most powerful ones we know about. So if your blood vessels constrict, that's going to cause your blood pressure to go up. Okay, so these are endogenous chemicals. Now, one more group of chemicals that affects your blood pressure over the short term. Since I'm a toxicologist, I have to mention nicotine, and I'm just going to pick another one, alcohol. Nicotine is an intense vasoconstrictor. And of course, nicotine is found in cigarettes and chewing tobacco and cigars and things like that. The way it works is that it stimulates the sympathetic nervous system, the fight or flight. Okay, it stimulates it. So this causes an increase in your blood pressure. And in fact, a lot of people who that have smoked cigarettes for a long time have an elevated blood pressure. They also have damage to their arteries, inflammation, and an increase in atherosclerosis. And one of the reasons is nicotine is such a powerful vasoconstrictor. Now, alcohol, on the other hand, it depends. Is it over the short term? So in other words, a couple of drinks on the weekend, or is it over the long term, which means a lot of alcohol, chronic abuse. Over the short term, alcohol inhibits the nervous system. And in particular, it inhibits the vasomotor center, at least that's one center. Now, of course, if the vasomotor center usually causes vasoconstriction, but if you inhibit it, you get vasodilation. And all over your body. And this is most visible in some people's faces. So people who have light colored skin, sometimes you only need one drink and their face turns red. And that is because the blood vessels in the face are dilating and the blood is filling them up. And you can see it because they have light skin. So vasodilation is going to decrease your blood pressure. So over the short term, alcohol decreases your blood pressure. But over the long term, it's actually going to increase it. And the reason for that, and this is, I just want to mention, this is chronic abuse. So this doesn't mean someone's having one glass of wine or 2 glasses of wine on the weekend. This means a lot of alcohol every day for years and years. In this case, what's happening, remember, is that alcohol causes inflammation of the tunica intima. And so over a long term, you're going to get atherosclerosis, plaque formation, which is going to increase your blood pressure. It also damages the myocardium. And remember this from the cardiovascular chapter. And over time, this is going to decrease your stroke volume, which is going to increase your heart rate. So a lot of people who are alcoholics have an elevated heart rate, and of course that increases your blood pressure. So this is regulation of blood pressure over the long term, and also some chemicals that have some adverse effects on it, over the short term, I'm sorry. But what about over the long term? Well, the major organ involved in controlling your blood pressure over the long term is the kidney. And there are 2 mechanisms the kidney uses. One is called direct renal regulation, and the other is called indirect renal regulation. Okay, so let's take a look at direct renal regulation. That's a little bit more straightforward. So direct renal regulation kicks in when your blood pressure is too high or too low, doesn't matter. And the main way it works is it changes your blood volume. Okay, so that's its main tool in the toolkit. It changes your blood volume. So let's say your blood pressure is too high. Then the kidneys will eliminate more water from your blood. So they'll move more water out of your blood into your urine. And your blood volume will go down and your blood pressure will go down. And that's how it works. So again, the direct renal mechanism, if blood pressure is too high, you just eliminate more water in the urine, and your blood volume drops, and your blood pressure drops also. What's an example? Oh, no, never mind. Let's look at this other one. Let's say that your blood pressure is too low. Well, then the kidneys are going to conserve water. So they're going to keep water out of the urine, keep it in the blood. That's going to increase your blood volume and increase your blood pressure. So an example would be perhaps during dehydration. So a lot of people get dehydrated when they're exercising, but you could also be dehydrated in the desert. Well, in that case, your blood volume is going to drop, and your kidneys are going to prevent the loss of water from the blood to the urine. That's going to increase your blood volume, increase your blood pressure. Okay, so again, direct renal regulation really involves just changing the blood volume. In fact, this is how a lot of diuretics work. They mimic what the kidney does. So if the blood pressure is too high, if it's very high, you'll be given diuretics. And diuretics cause you to eliminate more water in the urine. And that immediately drops your blood pressure. What about the indirect mechanism? Well, this just involves more steps. That's why they call it indirect. And it only kicks in when your blood pressure is too low, not when it's too high. So if your blood pressure is too low, the kidney's going to release a hormone called renin. Okay, so this is a hormone, but it is also a catalyst. Now remember, a catalyst is a chemical that speeds up the rate of a reaction without being used up itself. It is going to catalyze a reaction which results in the production of this chemical, angiotensin II. Angiotensin II is a potent vasoconstrictor. So right off the bat, you can see, oh, well, that's going to cause your blood pressure to go up. Now remember, in the beginning, it was too low. But it doesn't stop there. Angiotensin II also stimulates the release of aldosterone. And remember, aldosterone targets the kidney and causes it to reabsorb sodium. Wherever sodium goes, water follows. So your blood volume goes up and your blood pressure goes up. And it doesn't stop there. It stimulates the release also of antidiuretic hormone. And remember, this also targets the kidney. And it causes water to be reabsorbed back into your blood. So your blood volume goes up. And then your blood pressure goes up. And remember, the problem in the beginning was the blood pressure was too low. So angiotensin, again, is a pretty powerful chemical. It has multiple effects, right? Vasoconstriction is one of the major ones, but then it also stimulates two hormones that cause your blood pressure to go up. Okay, so we have blood flow through body organs, and that is something called tissue perfusion. And the purpose of tissue perfusion, the purpose of blood going to your organs, of course, is to deliver oxygen and nutrients, to remove carbon dioxide and waste, absorption of nutrients, for example, from the small intestine into your blood, and in the kidney to filter your blood. In this picture here, you can see in these columns, they're showing you how much blood goes to each organ. And of course, the total blood flow when you're at rest is 5,800 mils per minute. This is basically the cardiac output. Remember, cardiac output is the amount of blood flowing out of each ventricle in a minute. So this is saying that there's 5,800 milliliters of blood in the body. So when you're at rest, where is it going? Where is most of it going when you're at rest? Well, you'll notice most of it's going to the abdomen, right? And then we've got a lot to skeletal muscles, a lot to kidney, But then when someone is exercising, the blood is redistributed. So where do you see the biggest increase of blood? Well, if you said skeletal muscles, you're right. Skeletal muscle goes from 1,200 mils per minute at rest to 12,000 mils, 12,500 mils per minute when you're exercising. And that kind of makes sense. You want to redistribute the blood and send more to the skeletal muscles. You'll also notice skin goes up from 500 to 1,900. And remember that the blood vessels in skin are there to help you release heat and cool down. You'll notice a big decrease of blood going to the abdomen from 1,400 to 600 because you really don't need blood flow to the abdomen when you're exercising. So this is kind of important, but how does this happen? What determines where the blood goes? Well, believe it or not, it's the organs themselves, and this is something called autoregulation. Autoregulation is when organs regulate their own blood flow. Well, how do they do that? Two ways. One, they can change the diameter of the feeder arteriole. Now remember, down here we have a picture of the capillary bed, but the feeder arteriole is this one. So you can change the diameter of that. You can actually increase the size of this and allow more blood to flow in, more blood to go through the tissues. You can also relax or constrict the precapillary sphincters. Okay, so remember the precapillary sphincters are these little smooth muscle bands here that are at the beginning of each true capillary. Okay, so keep in mind, let's think about how this happens. So if this tissue, let's just say it's skeletal muscle, and this is during exercise, then you want more blood flow through this tissue. So what are you going to do to the feeder arteriole? Vasoconstriction or vasodilation? Well, if you said vasodilation, you would be correct. You want to make it bigger, so more blood flows in here. What about the precapillary sphincters? You would want to relax them, so more blood can flow to the true capillaries and gas exchange occurs. Okay, but what if instead you were exercising? When you're exercising, but let's say instead you just ate lunch. So if you just ate lunch, you don't want the blood to go to the skeletal muscle. You want to send it to the digestive organs. In that case, then, you would cause vasoconstriction of the feeder arteriole, which would send less blood here and more blood along to the digestive organs, and you would constrict the precapillary sphincters. And then the blood would go right through the shunt and bypass this organ. Well, how does that happen? Well, there are vasodilators. Now we've mentioned this one, nitric oxide. Remember that this is found in the tunica intima of all blood vessels, but it's also in this tissue here. So if we want the blood to increase blood flow to the tissue, the blood vessels themselves and the tissue itself releases nitric oxide, which causes vasodilation. But there are also other chemicals like potassium and hydrogen ions and lactic acid. These chemicals are also vasodilators, and they're released by the tissues during active exercise. So when your body exercises, it releases lactic acid and hydrogen ions and potassium, and that actually causes relaxation of these sphincters and vasodilation, and then the blood flows in here. So that's how that works. But what about vasoconstriction if you want to bypass that? Well, then we have the endothelins. And remember that these are released by the tunica intima of blood vessels, but it's also released by the tissues themselves. And so in this way, tissues are able to regulate the flow of blood to the organ. We are going to stop this lecture now. There are 2 more slides, but we're going to skip that.